Good morning, everyone. Welcome to another session of our pattern recognition exercise. Um, Before we start, does anyone have any questions or would anyone like to present their implementation of exercise 3? If you have any questions about the course or about the exercise, you can ask them at any point. But if you don't have them at the moment, let's get started right away. Um, Okay, let's take a look at exercise 3. So the first first task asks us to load the data. First two columns are coordinates of data points, and the third column is the cluster label. Implement the implement the following clustering methods and find clusters of this data. You need to have a preset of maximum number of iterations. Assume there's only two clusters in the data. Do not use existing implementations of these methods. So we need to implement k-means, mountain clustering, and subtractive clusterings by ourselves instead of using existing libraries. And you can find the formula for the formula for these methods on the lecture slides from page 9 to page 32. Um, you can also find the exact page number on the tips the tip slides that I have uploaded to the e-learn page. So the Euclidean distance formula is on page 6. Um, and the other formulas are around from page 9 to page 32. Okay, and we need to compare the performance of these methods and examine the effects of initial locations of clusters and different parameters. Just trying out different parameters. What kind of parameters are required for each of these methods to work? Okay, first let's take a look at the file. As it has said in the in here, we have three columns, and the first two are coordinates, x and y coordinates, and the third column is the class label. And to get started, we import NumPy, Matplotlib, and we import another library called itertools, so we can use it to calculate the product. First, we load the data. So original data. And then we load the points from the data. And first we select all rows, and then we select columns 0 and 1. This is This means to select columns 0 and 1, not including column 2. And then we load the data into an array. And here we're selecting all rows, but we're only choosing the third column, which is index 2, the third column. And you can take a look at them if they are loaded correctly or not. Okay, after loading the data, um, we should set two parameters for set two parameters for this. And it has already mentioned in the task here that we have two clusters. So we set cluster to 2, and we also need to set a max iterations. And you can choose a random number, but here we're setting it to 10 first. And this will apply to all three clustering methods that we will implement. And after we have implemented, after we have set the parameters, now we can define the first method, which is k-means clustering. And for k-means, we need two parameters. We get two parameters. One is the points, which are the coordinates, and then we need to set the number of clusters, which is 2 in this case because we have set the cluster to 2. First, for the k-means algorithm, first we need to select the initial centroids. K-means needs a starting point for the cluster center. So here we're getting the total number of data points, the length of the data points, and we're using random integer. We're using random integer to generate random integer indices between 0 and n. So the result of the centroids is a NumPy array containing coordinates of the initial cluster centers. And after we have selected a random initial centroid, then we need to assign each data point to the nearest centroid. So k-means will iteratively refine the cluster assignments and the centroid locations. So we create a for loop. And we we iterate them. We iterate the times that we have set before, the max iterations. Then we need to calculate the distance between each data point and each centroid. So we calculate the distance. And the Euclidean distance formula are in the slides if you need to refer to them. To the power of 2 on the axis of 1 for C in centroids. And we need to transpose them. Okay, so here we're calculating the Euclidean distance between the data point and the centroid. So it creates a matrix where each row represents a data point and each column represents a centroid. And the value in the matrix are the squared distances between the corresponding data point and the centroid. After we have calculated the distance, then we need to do the clustering. We need to determine the closest centroid for each point. Here we're finding the index of the minimum distance in each row of the distance matrix. So it assigns each data point to the cluster that are represented by the closest centroid. Okay, after we have done the clustering, then we need to update the centroids. So we create another for loop that's inside. Um, Here basically we're updating the centroid by calculating the mean of all data points that are assigned to each cluster. Clustering, here we're comparing, we're using a Boolean array of the same length as the number of data points. So it's true for the points that are assigned to the cluster C indices in the current iteration and false otherwise. And we're selecting only those rows from the points array that were assigned to the cluster. And so the result is a new array that's containing just the points belonging to the current cluster. And then we calculate the mean average of the selected points along the axis, which means along axis 0, which means to down the columns. And So then we get the calculated mean coordinates that are assigned back to update the position of the centroid for the next iteration. And here we return centroids. Okay, that's it for that's the function that we have defined for k-means. And then we need to define mountain clustering method. So for mountain clustering, you can imagine your data points as are all scattered on a map. Then you create an overlay. You create an overlay of the grid on the map. Then at each grid intersection, you calculate how popular it is by summing up contributions from nearby data points. So if there are more nearby data points, it contribute more to the popularity of the grid intersection. So you have to imagine this 3D landscape over your map where the taller it is, the more dense it is, and those are your mountains. Then you find the highest peak, which means the highest grid point in this map. And then you declare that location as the first cluster. And then you flatten the peak and the area around it using the parameters that we're gonna set later, the beta parameter. And after you have flattened this peak, the tallest mountain, then you look for the new highest peak in this modified landscape. And then you declare the highest peak as the second cluster center. And then you flatten this peak again. And then you repeat this step. You find the highest mountain, then you declare it as cluster center, and then you flatten it. You repeat this again and again until you have find the desired number of clusters. And the location of the peaks you found are your cluster centroids. So that's basically how mountain clustering works. And to do that, first we need a few parameters. First, we need the input points, the number of clusters, the number of cells. We give it a default value of 20, sigma, and beta. As we have said before, the points, the input here, the first parameter is the input data point. The input data point, which are the coordinates. Then the number of clusters are the number of cluster centers that you want the algorithm to find. The next parameter is the number of cells, which controls the resolution of the grid that's used by the algorithm. Remember the grid, the overlay that we talked about. It creates a number of cells by the number of cells grid. So a higher value, which means a more finer grid. So the resolution will be higher. A default value of 20, that means 20 by 20, that's a 400 grid points. So the higher it is, the higher the resolution of the grid. And next, the sigma, that's a parameter that we're using to control the influence of the data points when we are calculating the density, the initial density. A smaller sigma means only those points that are very, very close to the points that will contribute significantly to the density. So a larger sigma means points that are a bit further that will also contribute. And then we have a beta parameter. It's also for controlling the radius of the it's for the it's used for controlling the radius of the density reduction that's around a cluster center. So when we are flattening the curve, it will determine how much the mountain peak is flattened after it had been selected as the cluster center. So the default is also 1, but in use often the beta should be set slightly larger than the sigma. Okay, those are the parameters that we're gonna use for mountain clustering. And first, we should find the data boundaries. So we have minimum x, x. Okay, here we're trying to find the data boundaries. So we calculate the minimum and the maximum x and y coordinates from the input points. So it defines the boundary box that contains all the data because we need to use it to create the grid points. So the NumPy linspace, we have used this many times before. We are creating a creating the num cells evenly spaced values between the minimum and the maximum x values. And we're doing the same for y. So the product from the library that we have imported before will generate all possible combinations, which is what product means. It means the Cartesian product of the x and y values that are created by the linear space. And then we convert those combinations into a NumPy array. So now the grid points that we have here, holds the coordinates of every vertex in the number of cells grid that covers the data space. Okay, after we have created the grid points, then we need to calculate the initial densities. So we need to calculate the height of the mountain. And to do that, first, we initialize it. We create an empty array. Not empty, actually. We are initializing it to 0, to all zeros. So we have created an array. Um, we have created an array that store the density value for each grid points. And now it's all zeros. Next, we create the for loop to iterate through each grid point. So we're iterating through each grid point. And first we need to calculate the square distance, the square distances. Densities, IDX. Okay, here are the points minus grid points indices. We're subtracting the coordinates of the current grid point from all the input data points. And then we sum the squared, um, we sum the squared x and y differences for each data point. So we calculate the squared Euclidean distance between the current grid point and every input data point in the points array. And then densities. So again, NumPy exponent. This is the if this probably looks very familiar if you have done the exercise before, because this applies a Gaussian function, and the data points closer to the grid will yield a value that's close to 1. And the NumPy sums those Gaussian value over all input data points. So the result that we get here, it will have a very high value if many data points are close to the grid point. And it will have a very low value if there are not many data points. So this estimates the data density at each point. After that, we need to iteratively find centers and reduce density. So centroids. Again, we create an array to store the final cluster center coordinates. This just means It will have a number cluster of rows and 2 columns. And now we iterate the number of cluster times to find that many cluster centers. So if we want 2 clusters, we will find 2 cluster centers. First, we find the index of the grid point that currently has the highest density value. And then we store the coordinates of the highest density value as the the index cluster center. So after that, we need to reduce the density around this centroid to avoid from selecting it again. So basically, we're flattening, we're destroying the mountain. Grid points minus grid points, centroid IDX. That's divided by 2, multiplied by the beta to the power 2. Okay, here we're calculating the square distance between the newly found centroid, which is grid points, centroids, IDX. We're calculating this newly found centroid and all other grid points. And then it applies another Gaussian function. If you this looks familiar because it's another Gaussian function. We're applying another Gaussian function that's centered at the new centroid. But this time we're not using sigma, we're using beta. This is the second parameter that we use as the standard deviation. So it scales this reduction profile by the density value of the peak that had been found before. So it subtracts this scaled reduction profile from the density array. And that's how we are flattening the peak and reduce the density of the nearby grid points. So the same peak will not be chosen chosen in the next iteration. And this parameter beta is used to control the extent of the flattening, uh, the extent of the flattening. And finally, we also need to clip the densities because it's subtraction. We need to make sure no density values become negative after the subtraction. And after that, we return centroids. Okay, that's how we define the mountain clustering using the formula, the steps given from the lecture slides. And lastly, we need to do subtractive clustering. And it's somewhat similar to mountain clustering. Um, this time, this time, let's imagine a data point, all the data point that we have, but for but for each point, we are calculating how popular it is based on how many other points are close to it using the sigma parameter. So it gives each point a potential score that is based on the like how many other points are close to you. Then we find the data point with the highest potential score, and then we declare this point as the first cluster center. And to reduce the potential score of this chosen point and nearby points as well, we use the beta parameter to control the the range of the reduction. And um the amount of a reduction depends on the score, the score that of the point that we had chosen before. Then next we look at all the points again and find the new one, the one with the new potential, the highest potential score. And then we declare this one as the second cluster center. Then we reduce the potential score around this second center again. And we repeat this procedure until we have found the desired number of clusters. So the cluster centers you found are the actual data points from the original data set that were located uh, in the densest regions. So that's also the difference between subtractive and mountain clustering. Mountain clustering is calculating the density on an artificial grid that we have created. It's an artificial grid. It's an overlay. So centroids are grid points. So it's more computationally expensive if the grid is very fine, if the resolution is very high. If you set the number of cells to a very high number, um, it's more computationally intensive. And is less sensitive to the exact placement of the individual data points because it's on a grid. On the contrary, subtractive clustering calculates the density of at the data point itself. So the centroids are actual data points. It is less computationally expensive, so it's faster. It's a faster algorithm. If the number of data points is less than the number of grid cells compared to the mountain clustering. And here we have already defined, you already know what these parameters are for. So the first step is to set a potential centers to the data points. So we're not creating an artificial grid. Instead of creating the grid, we consider every input data as a potential candidate for it being a cluster center. So grid points here is just an alias for the input points. Again, initialize um, we initialize the density at each data point. This is same as before. So very similar to mountain clustering. First, we are calculating the squared Euclidean distance between the current data point and all other data points in the data set. So you can see it's exactly the same here. The formula is exactly the same. And after calculating the squared distance, we apply a Gaussian function again based on the distance. Points that are very close to the grid point, contribute close to 1. And points that are far away contribute close to 0. And the sigma here controls this fall off. And we sums up the contributions. And then like we did here, we initialize an array to store the final cluster centers. Here again, you can see it uh it is the same as the one here. We're calculating we're finding the index of the data point that currently has the highest density score. We can just use the same. Let's see if they're the same. Yeah. The density formula we have used here, density reduction formula, and the clipping. Then we return the centroids. Okay, that's how we define the subtractive clustering. After we have defined these three functions, now we can start to use them. We store them in clusters. And the input data are the points that we have imported before. Mountain clustering. And we have more parameters here for mountain clustering. Subtractive clustering, we have two. After we have run the algorithms, now we need to plot them. So we add a figure. And then we need to assign points to clusters. Um, First, we're calculating the squared Euclidean distance from each point to the center C. We transpose the array, so the rows are points and columns are centers. And we stack the distance. We stack the distance array into a single 2D array. And we find the index of the minimal distance for each point. So basically, here we are calculating the distance between the data point and all the centroids. So we can identify the closest centroid for each point, and then we assign cluster labels accordingly. So the algorithms here that we have run before internally assign points to clusters during its iteration. But the variables here only have the final center locations. So they don't have the specific, like which data point belongs to which center. That's why we need to do this assignment step for the visualization. And defining this is just the standard way is to define which cluster a point belongs to after the centers have been found is just assign it to the nearest cluster center. And that's why we're using the Euclidean distance here. Then we plot the data point using scatter plot. This first line, we are plotting the data points that are colored by cluster assignments. So X coordinates and Y coordinates, then the color that's based on the clustering array. Then we plot the k-means cluster centers in. Here's what I found. Sorry. Then we plot the k-means cluster centers. We are plotting them in red color. K-means clustering. And we can see this is what k-means had done. So you find two cluster centers, one here and one here. And this is the first cluster in color yellow, and the purple are in the second cluster. And because here we have defined it to random, so each run it will be random. It will use random initial uh a random point for to run the algorithm. So we run multiple times to see. We can see the classification is now very good. The cluster centers they found is also not very accurate. But let's continue plotting the rest of the rest of the result that we have. We need to plot mountain clustering. We add another figure. We use the same assignment steps. But we change it to mountain clusters. Maybe you can also give it a deep green color. And you can see here, this is the result of the mountain clustering. And the result also looks very bad. It's somehow even worse than the k-means clustering because almost all the points are belong to the first cluster, and just these tiny little points are to the second clusters. Let's continue. Let's do the mountain clustering methods. The subtractive clustering method. Maybe you give it a pink color. This is slightly better, slightly better than the ones we had before. But it's still not good. But here we can already see the k-means after multiple runs, even with random initialization, the results are always end up in similar results. But for mountain clustering and subtractive clustering, we have these two parameters that we can set to improve the result. So now we set the sigma and the beta to 5, and let's see if the result improves or not. We can say mountain clustering are still pretty bad, and subtractive clustering got worse. Before it was better than this. So let's change the parameters again. Let's increase the sigma and beta to 10. And now we can see the mountain clustering has improved significantly. There are still some errors here, but it's a lot better than the ones we had before. And let's see subtractive clustering. And for subtractive clustering, the result is even better than the mountain clustering. We can see here around this part, they only got a few points wrong. So by comparing these methods and different initial locations and different parameters, we can say that um, mountain clustering and subtractive clustering, and especially subtractive clustering, outperforms k-means for this data. And that's also the benefit, or it could be an advantage or disadvantage when you're thinking about this, that you can set your own parameters for the mountain and subtractive clustering, because you are able to modify the the algorithm's behavior with those different parameters. But for k-means, you cannot. Okay, that's it for task one. Let me know if you have any thoughts, or if you have any thoughts, any comments, any questions that you would like to ask. If now we can take a 5-minute break before we continue on task number two. Um, you can grab some water if you need. Let's come back around 17, 5 minutes. Okay, we're back. And let's take a look at task two. So the task is to load the data butterfly.txt demonstrated in the lecture. Um, we implement both k-means and fuzzy c-means clustering methods with the number of clusters set to 2. Examine clustering results of 0.32 in different trials. Do the clustering results change between different trials, and which one will be more appropriate clustering method for this data and setup? Set the number of clusters to 3 and repeat the above experiment. So the main goal is to apply k-means and fuzzy c-means. So we have already, and let's take a look at the data first. So they're just coordinates, x and y coordinates. Uh, we have implement we have implemented k-means before. So now we just need to implement fuzzy c-means. And what fuzzy c-means is, it's like k-means, but k-means in k-means where each point belongs entirely to one cluster. Fuzzy c-means allows points to belong to multiple clusters simultaneously, but with different degrees of membership. So we define fuzzy c-means clustering. And we need points, number of clusters, and an M parameter. Um, the points here are input points, number of cluster, um, the number of clusters that you want to find, and M here, M parameter is the fuzzifier, or or you can call it the fuzziness exponent. And this is the parameter that controls how fuzzy the cluster boundaries are. So M, you can check the formula again in the lecture. There are very specific steps to how to implement them and the formula. So when M approaches 1, the clustering becomes crisper. The boundary is harder compared to k-means. And as the M parameter increases, the clustering becomes fuzzier. So its membership are more evenly distributed. So that's the parameters we need. First, we need to again initialize cluster centers, and we use random uniform. Okay. Here again, we are we are initializing the cluster centers, but we're picking the number of cluster random points within the boundary box of the input points. And then we need to initialize the membership matrix. In the formula, you will see this as U. So weights. So the weights here will eventually store the degree of membership of the point in the cluster. So if we see them like this, so I is the point and J is the cluster. It will store the degree of membership I in cluster J. It's initialized with random values between 0 and 1. So one thing to be aware of is that these initial random weights don't necessarily sum up to 1 for each point yet. But the algorithm will fix this in the first iteration. And we need to repeatedly update the membership weights and the cluster sense weight until they stabilize, or until the number iteration is reached. We have already set the max of iterations earlier. So we use that parameter as well. And we calculate the distances again. Typo there. Okay. I think we have explained this formula before. We're calculating the Euclidean distance between the point and the centroid. So we're not gonna, maybe we don't need to explain it step by step. But the next step after we have uh, calculated the distance, we need to update the membership weights. So we create create another loop. And you can find this formula on the lecture slides. I will explain it later. Okay, let's go through this formula step by step. First, the distances. This is the distance of all points to the current cluster C. And it just means shape and point. So the none here adds a dimension for broadcasting. And distance that's divided by distance at 1 exponent minus 5. This is divided. It just means a very, very, very small number that we're using here. And the reason we need to add this is because this very small number prevents the division by 0 if a point that happens to if this point just happens to lie exactly on the centroid. So this very small positive value is 1 to the exponent of minus 5. So it's a very small value, but it's positive to every calculated distance before it's used in the denominator of the ratio. So this can ensure the value can never, the denominator can never be exactly 0, even if the true distance is 0. So we need this, we need the stability, numerical stability during this step. Okay, after we have updated the membership weights, then we need to update the centroid. Um, okay, let's take a look at this centroid update formula. First, weight to the power of m. We're taking the membership values for cluster C. We're taking the membership values for cluster C and we raise them to the power of m. Then it multiplies each point's coordinates by its fuzzy membership for cluster C. So the points with higher membership in cluster C will contribute more heavily. And the sum here, the numpy sum, sums the weighted coordinates over all points. So it is the numerator of the weighted average. So and then we sum numpy sum. The numpy sum here, the numpy sum here sums the m-powered weights for cluster C over all points. So the result of the new centroid C is the weighted average of all points, where the weight of each point is determined by its degree of membership in the cluster. Okay, after we have updated the weights, the membership weights and the centroids, then we need to do a post loop calculation. So we calculate the distance again. We can use the formula we have used earlier. And we calculate for C. This is same as the one before. And we return centroids and weights. And the reason we need to do this is because the loop finishes after updating the centroid in the last iteration. Here. So the weight calculated inside the last loop will based on the previous centroid position. So here after the loop, after the loop, we repeat the distance and the weight calculation one last time using the final centroid positions that were determined by the loop earlier. So this ensures that we can get the return weights are consistent with the return centroids. Okay, now we just need to plot them. We run k-means cluster. We need to find 2 points. After we have run the algorithm, then we can start plotting. So we first add a figure. And then as we have done it before, we first need to assign them to the clusters. So k-means. Okay, this is the formula we have used earlier. So we're just gonna continue using that, and then we plot k-means. And we set the size of the marker to make them larger. Okay, we can already see the k-means. Then we need to plot the fuzzy c-means overlay. And the color is based on the fuzzy weights. And we can see it again. Okay, this is the result of the fuzzy c-means. Then we need to plot the centroid. And we plot the centroid for fuzzy c-means. And we can see the the centroid for fuzzy c-means is blue, and the centroid for k-means is in red. And oh, sorry, we used this on the wrong data. So we need to we haven't we used it on the first data. And now let's try them on the second data. Just a second. Okay, let's see them on the butterfly. On the butterfly data that we need to plot. The algorithm we have already defined here before, and now we are using the algorithm on the butterfly data. So here, the red ones are the k-mean center, and the blue ones are the fuzzy c-mean center. Let's comment them. First, let's see the k-means. We can see the data have been separated into two clusters. The ones on the one cluster, second cluster, and we need to examine the clustering results of the point 3, 2 on the coordinates. So it's this one. This exactly one in the center. Let's look how they behave in different algorithms. We run them multiple times. We can see sometimes the one belongs to the first cluster, and sometimes they belong to the second cluster. And that's for k-means. And as for fuzzy c-means, you can see it's giving it a green color. So it means some part of it belongs to one cluster and some parts of it belongs to another cluster. It belongs to the first cluster at some degree and it belongs to the second cluster to some degree. That's how the algorithm interpreted it. And we can also do this for, let's go back and change the iteration to 3, to clusters to 3. We repeat it for 3 and see if it changes anything. Okay, let's change it here. And now the k-means is trying to calculate 3 clusters. And we can see it separated this one as a one cluster, this as one, and this part as one. And for c-means, it doesn't change much. Fuzzy c-means. Okay. So how do you interpret this? So k-means is very sensitive to the it's usually sensitive to the initial placement of the centroid, but here we can say every time it gives almost the similar result. Fuzzy C means Fuzzy C means calculate a degree of membership for each point belong to a cluster. So here, fuzzy C means is more appropriate when the cluster is two, because the center point shouldn't belong to either it shouldn't belong to cluster one or cluster two. Um, it gives a 50-50 share to belong to both classes. When we have three clusters, the result vary from run to run. Um, and fuzzy segments doesn't do much here, doesn't make much sense here. Okay, that's how we interpret those results. We tried it twice, once with two clusters and once with three clusters. Okay, that's the butterfly. That's for the butterfly data. Um, do you have any questions for today's session? If you have any questions, you can ask me here, or you can ask me in the chat or send me an email. But if you don't have any questions, then that's it for today's session. I will upload the videos to the eLearn page later. And thank you for coming to the session. Thank you.